In this video, I want to introduce you to an application of infinitely repeated games. We're going to consider collusion in repeated oligopolies. Specifically, we'll start with the Chrono Model. You know the Chrono Model well at this point. There are two firms. The price in the market is given by 1 minus Q1 minus Q2, where Q1 and Q2 are the quantities selected by the two firms, firm 1 and firm 2. To keep life simple, we'll have the marginal cost equal to 0. So given the setup, the profit of firm I, given quantities Q1 and Q2, is the price, which is 1 minus Q1 minus Q2, times the quantity that firm I produces. That's the revenue, but as there's zero marginal cost, there isn't a cost of producing the quantity Qi. Since you're quite familiar with the Chrono model, we won't go through solving the Nash equilibrium of this stage game, but if you go through it yourself, you'll find that the Nash equilibrium of this Chrono stage game, if we played it as the one-shot game, would be for both firms, firm 1 and firm 2, to select the same quantity, which is a third. That leads to an equilibrium price of 1 minus third minus a third, so that's just 1/3, and the equilibrium profit for each firm, so the price times quantity, which is a third times a third, which is 1/9. So that's what the duopolists will do in the stage game if it's a one-shot interaction. What would a monopolist do here? The reason we ask what a monopolist would do is because the monopolist is making a decision that maximizes the firm's welfare. So the monopolist isn't constrained by competition. If the two firms could coordinate to do what the monopolist does, they would be better off. The monopolist is going to choose Q to maximize total profit, which is 1 minus Q times Q. The first order condition is 1 minus 2Q equals 0, so Q equals a half. So that's the total quantity that the monopolist would produce. So firm 1 and firm 2, if together they produced the quantity that the monopolist would produce, they would be better off. Really, they could pick any Q1 and Q2 that sum to half. Then the total profit would be 1 minus a half times a half, which is a quarter. They could split that. If they both produce Q1 equals Q2 equals a quarter, they would each get 1/8, which is greater than 1/9, which is the profit that they get when they compete with one another. Or they could pick some other distribution Q1 and Q2 such that the total profit is a half, and they could still split it such that they both get at least 1/9. But let's focus on Q1 equals Q2 is a quarter, then they each get a profit of 1/8, which is higher than the profit they get when they compete in the Chrono game. So by coordinating, in other words by colluding, to restrict the quantity to a quarter rather than a third, they can do better than the stage game Nash equilibrium. However, we know that when they interact only once, they can't sustain that as an equilibrium because they both have an incentive to produce more. An important question is, in reality, do competing firms only interact once? Is the one-shot interaction the more realistic model for how firms compete? And the answer is no. Typically, firms interact repeatedly over a long period of time. So we could better model this as a repeated game where there are many periods where the two firms interact. So the firms could then sustain collusion, so Q1 equals Q2 equals a quarter, as a subgame perfect equilibrium. They could just use a grim trigger strategy. They could say, okay, we will play the strategy of restricting quantity to a quarter until one of us cheats. As soon as one of us cheats, we'll revert to the stage game Nash equilibrium and produce a third. And we'll do that forever. So let's check that this grim trigger strategy, where the two firms produce 1/4, as long as they've always produced a quarter, and otherwise, so in other words, if somebody has cheated, they switch to 1/3 and they produce 1/3 forever. Let's check that that's actually a subgame perfect equilibrium. If you recall from the earlier videos, we do that by using the one-shot deviation principle. We check if in any period t, firm I would have a profitable deviation in just that one period. Now we need to check that in any period t, firm I doesn't have an incentive to deviate in that one period, and we need to do that regardless of the history. So we need to check for all possible histories. So let's start first with any history where only 1/4 has ever been played. After such a history, if firm I chooses to set their quantity at a quarter, then their period t payoff, so their profit in period t, is 1/8, as we saw earlier, and their period t plus 1 continuation payoff, so their lifetime profit starting in period t plus 1, would be 1 over 8 divided by 1 minus delta. So the total profit would be 1/8 plus delta times the continuation, so it's 1 over 8 times 1 minus delta. However, if the firm deviates, unlike some of the other examples that we've seen, here firm I could do many things. It's not just one deviation we need to look at. However, what we can do is we can just check what delta needs to be for even the best deviation from qi equals a quarter not to be beneficial. So if firm I deviates, we know that the continuation payoff in the future is going to drop to 1/9 in every period, because now these strategies are triggered and both players switch to quantity 1/3. So the profits in every future period drops to 1/9. So the continuation value starting period t plus 1 becomes 1 over 9 divided by 1 minus delta. But we need to figure out what the best deviation is in period t. And that best deviation would be the solution to maximize your profit. So choose QIT to maximize your profit. What's your profit? The other firm is producing 1/4 because that's what the Grim Trigger strategy tells them to do. So the price, if you produce quantity QIT, is 1 minus 1/4 minus QIT. So your profit is the price times the quantity you choose, which is QIT. So the first order condition is 3/4 minus 2 QIT equals 0. That means that QIT is 3/8. So the best period t payoff that firm I could get when they deviate from a quarter is 1 minus 1/4 minus 3/8 times 3/8. That's 9 over 64. So the total is the period t payoff plus delta times the continuation. So it's 9 over 64 plus delta times 1 over 9 divided by 1 minus delta. So that's delta divided by 9 times 1 minus delta. So with the total that firm I gets from sticking to the Grim Trigger strategy in period t is 1 over 8 times 1 minus delta. The best that they can do if they deviate is 9 over 64 plus delta over 9 times 1 minus delta. So for this one-shot deviation not to be beneficial for firm I, it has to be that the payoff from sticking to the Grim Trigger is at least as high as the best payoff that they could get from deviating. So let's do some algebra to simplify this into a nice condition on delta. This is equivalent to 1 over 8 minus delta over 9 divided by 1 minus delta. Has to be at least 9 over 64, which is in turn equivalent to 64 over 8 minus 64 over 9 times delta, being at least 9 minus 9 delta. So 8 minus 64 over 9 delta is at least 9 minus 9 delta, which is equivalent to 9 minus 64 over 9 delta is at least 1. So that means delta is at least 9 over 17. So if the firms are patient enough, so delta is at least 9 over 17, which is a little more than half, then they can support collusion as a subgame perfect equilibrium. So as long as they're patient enough, they can collude in equilibrium and behave as a monopolist. And we saw that repetition enables collusion. But this phenomenon is actually more general. Even for other oligopoly models, you can show similar results. So as an exercise, think about the Bertrand model. Remember that in the one-shot Bertrand game, both the firms are going to compete so intensely that they're going to set the price equal to marginal cost and end up with zero profit. Now think of a very simple version of this game where there's a demand of 100 at any price that's no greater than 1. And as usual, if they set the same price, they share the demand. So they each get 50. So show that they can actually support collusion and they can support the price of both setting the price P equals 1 and split the profit as a subgame perfect equilibrium. So they can support collusion even in the Bertrand model. The analysis is going to be very similar to what we've done for the prisoner's dilemma, for this Chrono model. You're going to show that the Grim Trigger strategy will do the job. We both agree to set the price equal to 1, but as soon as one of us deviates, then we're going to revert to the stage game Nash equilibrium, and we're both going to end up with zero profits in the future, which we don't want. So as long as we have this punishment available to us, which is the ability to set the price equal to 0, that helps us a lot in sustaining the collusive equilibrium. Now, this type of collusion is typically illegal. In Canada, we have the Competition Act, which forbids it. We even have a federal agency, the Competition Bureau, that's responsible for enforcing the Competition Act. Nonetheless, in equilibrium, players don't actually sit down and make an explicit agreement about their strategies. They're usually just implicit agreements. Of course, even that is still illegal. Nonetheless, it's very difficult to prove. So we often see these types of anti-competitive practices all over the place. Perhaps some of you remember, a few years ago, we saw Loblaws had to give out $25 gift cards because for many years, them along with the few bread producers had been setting the price of bread higher than they should have been. So the means of collusion was along the lines of what I'm asking you to do in this exercise. Another example of this type of collusive behavior, even though it's very well disguised, is the price match guarantees that you see when you go to many stores. This is actually an example of a tit-for-tat strategy, which is a less punishing strategy than a grim trigger strategy. On the face of it, it seems competitive. However, what it does in the long run is that it's announcing that I'm setting a high price, and I think you're going to set a high price too, but if you set a low price, then I'm going to do a tit-for-tat and set a low price as well. And that's enough punishment to prevent you from lowering your price too much. These type of tit-for-tat strategies are less punishing than grim trigger strategies, but they're still effective in sustaining cooperation. So the point is that these long horizons over which players interact really change the dynamics of the game that they're playing, and we can see a much richer set of outcomes that arise. And when it comes to things like competition, it's very difficult to recognize or to pin down collusive behavior, and it's actually quite easy to sustain collusive behavior in these types of repeated interactions.